we've got one project left to do, and it turns out this one is actually pretty involved, but we're gonna get through pretty much all of the calculations here. That's kind of the good news. It actually pulls in just about everything we've been doing with these financial calculations in Chapter 6. If you read through it, we end up using something from compound interest, from annuity future values, and amortized loan stuff, which kind of relies on annuity present values. So there's an awful lot floating around in here. So initially, and funnily enough, the very first bit is probably the trickiest part of the whole thing. The rest of it you can sort of suss out just by pounding through the various formulas and stuff that we've talked about in the various sections of Chapter 6. So we've got ourselves a construction company. They're planning on building a new building, if I recall correctly. And they're trying to set aside money for a down payment so they can start construction, which is funny. Construction company starting construction on something. Whatever. All right. So we know that they're putting money aside here. So on the one hand, we've got an annuity present value that's basically building up. So each month they're planning on putting aside $2,000. So for this first guy, we've got an annuity, just ordinary annuity, present, as you said, or future value rather. We don't need present values for this. My apologies. So we're told they're putting away $2,000, and now we can just use the ordinary annuity future value formula to work out what's going on here. We need we need N technically, but N is actually going to be the guy we're after. So if we come off to the side here, the interest rate they're getting is 6%, and they're making monthly payments. So usual routine at this stage, we take our annual rate, divide it by 12, because this is a monthly thing, and we get an I value of 0.005. I'm trying to keep my head out of the way so you can see it. Now we've got I, we've got our payment plan, value R, and we just kind of fill in the rest. So we have 1.005 to the N. Like I said, N is our unknown here. Minus 1 divided by 0.005. All right, so that's what's going on the one hand. The problem is they're kind of aiming at a moving target because inflation is a thing, because inflation is virtually always a thing, and the amount they actually need, it starts out at 500,000, but they're assuming an annual 3% inflation with the same sort of monthly compounding we're dealing with here. So this is almost, you can basically treat it as a compound interest problem. It's, technically not actual money that's there, but that's essentially what's happening. We've got this lump sum value that keeps going up as time goes on. So we've got this value. Then on the other hand, we're kind of aiming at this formula that's supplied by the text of 500,000 is how much they're initially planning on spending, times a different I, because the inflation rate is only 3%. So fortunately, I guess their annuity is gaining ground on inflation. So here we've got a different I, 0.03 divided by 12. That's going to be 0.0025. So we have 1 plus this I. So yeah, I'll just go with it in the interest of time. The bracket is not necessary, but so we have 1, this guy, also going up to the end. So now the catch is, their down payment's not this whole thing. They're not trying to save up for all of it at once. They're planning on doing some financing. So they need 20% of this, though. So that's, 0.20. So let's do it that way. So we've got those two things running alongside each other. Technically, 0.2 times 500,000 is 100,000 if you wanted to cut this down calculation-wise. So we got that part done, which is all well and good. The trick is, now we want to know how, so we're trying to find value of N where this is equal to this. Please don't try to do that by hand. It's not going to end well. So there's a few different ways you could go about trying to get a solution to this particular, equation. This thing equal to this thing. Like I said, I don't recommend trying to do by-hand algebra. That way lies madness. So there's a few different options you have. as it turns out, our old friend Excel, who comes up in most of our projects, uh, so it has a tool within it called GoalSeek. Our text actually has a description for how to use the GoalSeek tool. That's normally how I would do this if we were face to face in a classroom together. I'd have an Excel window pulled up, with these formula calculations. We walk through how GoalSeek gets us a value for n. That's an option. Um, you could also technically graph this, use x instead of n in a graphing calculator, use x instead of n here, have them as two separate things, and then find their point of intersection like we did when talking about linear programming stuff, using that intersect tool in the calculator. While we're talking about graphing tools, I guess you could actually just graph both of these things inside Desmos, find where the curves cross, and Desmos kind of gives you, the coordinates of the point of intersection. So you could use a calculator tool, you could use Desmos, and find the intersection. Like I said, there's a slew of ways you could go about this. So we've got each of these guys. Now, again, I don't, require you to go through all of the algebra. Like I said, it's not, it's not really a tractable problem algebra-wise. What I would expect in this scenario is when you're writing up your report, describe which method you would use to find the value of n that ends up popping out of this thing. That's what I'd like for you to see. Describe using Excel's GoalSeek tool. Maybe that's a business standard thing using Excel, so that makes sense. You could also describe how you track this down using graphing calculator technology. I just want to see in your report a description of how you would go about finding this n. And again, don't try to do it by hand. Any case, so one of these methods, when it's all said and done, is going to end up giving you an n value that's approximately 50 payments. So it's going to take them a little more than 4 years in order to work out, what they're going to end up needing. Okay, so that's actually problem one. Identifying that value of n and how long it's going to take them to save up is the entirety of problem one. Cool. Okay, so we got that taken care of. So now, the second problem is relatively straightforward. It's actually, I'm going to sort of, try to reuse some of the stuff that's already here on the board for problem two. Because part two says, all right, assuming that they're accurate on inflation, nothing weird happens, what's the total construction cost? And it says round to the nearest $100. All right, so now we can erase this 20% but this was our figure for how much it's going to end up costing the company, right? 500 grand times our, periodic inflation thing raised to the n. We now know the value of n that comes out of this thing. So we can take this, feed it in right here. And so we have 500,000 times this 1.0025 term raised to the 50th power. When we work that out, it does say to the nearest $100, so that's a kind of a change of pace. We're not having to worry about the nearest penny this time around. I got $566,500. So yeah, that's how much it's going to end up costing the company when it's all said and done. So we've got that part taken care of. We've done, it feels like half the project at this point. There are 4 problem parts, and we've resolved 2 of them at this stage. Okay, now for the next part 3, which feels weird that I'm writing it above part 2, but small board, you know the drill by this stage, right? All right, so they're planning on financing 80% of this because they socked away the 20% down payment. So we need to work out 80% of this figure. So 80% of the total cost. When I work that out again to the nearest 100, I don't think I need to do any rounding in this instance. I got $453,200. Feel free to double check and confirm that. Show the calculation as part of your write-up. All right, so that's how much they're planning on having to finance. All right, and we're given their amortized loan information after this. So they're basically kind of taking out a mortgage of sorts on this thing. So their interest rate is 7.8%, and they're making monthly payments over a course of 15 years. So this thing is essentially their A sub n in that amortized loan payment formula. All right, so their annual interest rate is 0.078. sorry, their annual interest rate is this. To get the periodic rate, we got to divide by 12 because they're making monthly payments. When I did that, I got 0.0065. The N in this instance, they're doing 15 years, 12 months in a year, so they have 180. So now we've got all of the relevant pieces to feed into that amortized, loan payment formula that we saw in section 6.5. So we have, can't write, 453, 200. Up top, we've got 0065. Down below, again, I'll enclose this in parentheses like I've been doing, the whole time. 1 minus 1.0065 to the negative 180. Close up those parentheses in the back. So just like we saw in section 6.5, we've got everything more or less in a line. So long as you have these parentheses right here, you can just type it into your calculator in one big row. Alternatively, if you wanted to use an Excel setup, we've already talked about how you could use Excel for the goal seek thing, so that's a perfectly valid, process here. When I pounded this whole thing out, I got a monthly payment of $42.78 and 85 cents. So this time around, we do keep it to the nearest penny. So, all right. So we've done part 1. We've done part 2. We've done part 3. That leaves part 4. I can't fit part 4 into the rest of this video, so look for another one momentarily where we work through the last bit of that, and then we'll talk a bit about what's going on with this project, your write-up, and whatnot.